have Vinija with us today. So Vinija recently switched her job and she is at Google now. And I think you're a staff engineer at Google now, right?
Yeah, yeah.
So amazing expert voices we have with us today. And thanks for joining us, Vinija. This is thanks for your time. A lot of effort and a lot of energy and time goes into preparing all the content and bringing these webinars to all of you. So thanks, Vinija, for putting in the time and energy. We really appreciate it here at Single Store. And for everyone that has joined us live, we hope that you have a great experience. This webinar is it's about MySQL and how to scale without basically the gist of it would be about cutting the cost. I hope I'm correct, right?
Yeah, yeah,
so
yeah, absolutely.
so yeah, and that's like the basic gist. Obviously, Vinija is the expert, and I would leave all of the jargons to her. And I hope you all enjoy. I will just keep an eye out that you are currently in a listen only mode, and I will be communicating anything using the chat button that you might see. If you have any questions, we will have a dedicated Q&A session that will happen during the end of the session. So feel free to stay if you want to get your questions answered live. We also recommend that you follow along in real time. And if there's any resources that you would require, Vinija, feel free to share if there's any GitHub link or
Yeah,
anything with me,
absolutely.
and I can share that to the audience. And guys, keep an eye out on the chat, and you'll see everything from me there. Uh, I'll also send a link to try Single Store for free. So we are offering $600 worth of free credits, which last you pretty long. So there's no credit card information required, anything. You can just sign up and get started. Vinija will explain how she has actually built the demo around it. So yeah, to make the best of your time, we would highly recommend that you follow along. And yeah, um, please, I hope make yourselves comfortable, and I'll hand it over to Vinija now. Okay, thank you.
Awesome, folks. Thanks so much, Yukti. And I can start sharing my screen. So the credits Yukti mentioned, I would definitely sign up for that. And actually, I've used them quite a bit in the past. I think it's a great resource. So you'd be surprised how much $600 gets you, but it's a great starting point, a great POC. The other thing I really liked was that there's a whole gallery of notebooks available. So you don't really have to start your code from scratch. There's a lot of resources there that are already provided for you, which is a great starting point for, any project that you're looking to work on. So welcome today. We're going to be chatting about MySQL and how to scale it. We're going to go from a single instance to even looking at real-time architectures. We're going to look at some common MySQL scaling problems. We're going to have a quick live demo here. Some real world case studies that are going to go on, cost-effective solutions, and migration strategies. All of that is what I'm looking and hoping to cover, and would love to answer any questions towards the end of the demo. For today, I thought we'd do an interactive website rather than slides. I think it would be kind of a more intuitive, more informative. And I have the code, of course, for this. This is deployed on Streamlit and available, and I can share it with Yukti if you'd like to take a look as well after the call. So yeah, so this is where we're going to start with the performance overview first. And what we're looking for here is overall, what we want to do is talk about the different strategies here that is going to help us scale our MySQL applications, scale them in a way where we're able to give the max utility, max users are able to use our end database without being throttled, without having efficiency losses. And what I've seen in my career and what some of the kind of solutions that I've also helped deploy in my career. So first, let's start with the performance overview here. All right. So with performance overview, I've kind of created this interactive demo, and we'll explore this together. Basically, what I'm looking to do, this dashboard has a few different things. We have the response time improvement here, which will basically go from 1,900 milliseconds to 95 milliseconds. We have the throughput increases here. We have cost reduction laid out here. We have uptime improvement here. And these aren't just theoretical numbers. These are real results from real case studies that we'll also go over today. So that's the improvement here is quite impressive. And the charts you'll see here, what they're showcasing is the response time based on the architecture type that you've used here. Right. So, for example, the single MySQL application can have quite a high response time, as you can see in the tail end. But even the average response time is quite a lot higher than what you'd see, say, with read replicas, where you've added some slight improvement onto your prior application. Even with caching, so now you've added Redis caching, which means you have taken your kind of most hit queries and you've stored them so that users don't have to query the database over and over again. That's also increased your response time. And hybrid architectures. And hybrid architectures can mean a variety of things. It can mean having, a cache readily available and read replicas, multiple different various things. Maybe you also have microservice architecture, so you have multiple MySQL databases. Usually we see a better response time with something like that. Also laid out throughput scaling here. So what we're seeing here is concurrent users and the QPS. So the line here will represent, MySQL. It's just a single MySQL instance, and you see the variability there versus a scaled architecture where you're able to increase QPS along with the concurrent users that you're getting, which is critical because as you increase your user base, you need to be able to accommodate for that. All right, so that's just a high-level overview. Now let's sort of get into the meat of things. So let's start with our first use case here, which will be the query optimization. Query optimization is kind of the lowest hanging fruit that you'll have, right? That you can start working on to help scale and help optimize your database. There's a lot of, different ways you can write very slow queries. I have a quick example here where you're basically just looking to, select your name, email, the username, email, then the total and an amount from the user's database joined with the orders database on the user's ID, joined on the payments as well. And then you have your other conditions where the users were created before a certain date and the order status is completed. And you want to order and you want to, order it by descending when the order was created at. So at a first glance, this seems, very simple, logical, but there's a few issues here, and these few issues will cause it to actually slow down. First of all, there's no proper indexes here, right? So you need to have indexes done on your on the few columns that you're going to kind of hit the most here. You have very complex joins without optimizations, and you're actually looking at doing the full table scans. So this query, like we said here, can take, multiple seconds to execute, which we can easily fix with a simple optimization strategy. So this is going from a 2.3-second execution time to now we're going to a 0.15-second execution time. And here's the few things that we've changed here. First, we've added the indexes, right? So you've created the indexes on the user's creation status on the user itself. So what we're looking to order it at is the created at date, right? The order when the order was created at and the status. Those are the two critical filters that we want to be able to use to filter our data out. So it makes sense to create the index around that. The second is on the order itself, because as we're looking to pull the order, we will need to be able to use the user ID, the status, and the created at date again. So it makes sense to add indexes on both of those tables for these columns here. Now, once that's done, then you can almost have the identical query here where you're selecting the user's name, email, the order total, the full amount here, the payments amount from the user, from the order, and you join it on the payments table, and you have your same filters, order by. Now, in addition to that, what I've also added is a limiting factor. So that also obviously helps limiting the amount of data that you're looking to get back as a return there. Sometimes, especially as you're executing early on, you want to limit it to a smaller amount just to be able to do a quick smoke check and make sure the data is exactly in the format and what you were expecting. But also otherwise, in terms of your applications, if you're able to add a limit, it definitely helps in the optimization there. So what we've done here is we've made sure we've added the correct composite indexes. We've limited the query results, and we've kind of optimized the join order here as well. So we're taking it from users, we're joining it on order, and then we're also looking to join on payment, which is very similar to what we did earlier, but because of the indexes, our retrieval will be a lot faster. And also wanted to share some performance results here. So here are just some metrics that are, critical when you're looking for optimizing your queries. First of all is the execution time. So before, when I ran this locally in my MySQL database, I saw it took about 2.3 seconds to return. And after, it was just 0.15 seconds. So that's a 15x improvement already with the simple changes that we did. CPU usage as well. Before, it was at somewhere about 95%. Later, it looked to be around 45%. So that's a 53% decrease in CPU usage. For memory usage, it was at 90%, and then there was a decrease to 60%. So that's 33% less usage. Rows examined was also looking at 1,000x less than what we were looking at earlier, which is great for efficiency overall. And a quick demo here. So just running a quick query optimization, the slow one took 2.3, and the optimized one took 0.15 seconds. So yeah, it was definitely 15x faster. All right, so that's the lowest hanging fruit, query optimization. Let's look at the next one, and that's connection pooling. I've seen this quite a lot in my career, and this is, again, a very simple fix that you can do within your end to sort of help optimize your database applications. So connection pooling, when you're creating new database connections, for each of the requests that you're sending to the database can be expensive and can lead to connection exhaustion. So connection pooling, what it basically does, it helps you reuse the connections and dramatically improves the performance and the resource utilization there. So without connection pooling, basically each request you send to the database will create a new request. So imagine this is a function within your microservice where you're looking to get user data. So you pass it a user ID and you start your MySQL connection. And you basically run your query, and then you store your results, and then you close the connection. It's very simple. There's nothing wrong with the code. It will execute. The issue comes in the efficiency and the performance here, where you have high connection overhead. The connection pool will be exhausted, and there will be resource waste. Now, with connection pooling, what you can do is basically reuse your connections from the pool itself. So here are the two libraries that you should know for that, and that's both are in SQL Alchemy. Basically, there's Create Engine and QPool. And what you'll do with the engine is you'll, like before, you'll create your engine. You'll kind of specify your pool class, which is your QPool. You can specify your pool size here, your max overflow, your pre-ping, any of these criterias that fit best for your use case. And now, once you've defined your engine, now what you can do is instead of opening the connection, you can just call the engine and ask it to connect for you. And what it'll do is basically then you'll be able to store your results for your specific query, and then just sort of return those results there. So now in this case, what you're doing is you're letting SQL Alchemy manage the connection reuse. So you, at a bare minimum, have a better resource utilization and kind of automatic connection management as well. And just some charts to show you performance comparisons, where the green one is the connection pooling, and the red is the direct connections. You could see total execution time is quite higher, especially as you increase the number of threads, which naturally makes sense here. Whereas for connection pooling, even as you're increasing, the minimal execution time is not increasing as dramatically as it would without connection pooling. And a quick look at a demo here as well. So say you have number of queries at 100 and number of threads at 10. So let's look at what connection pooling would help us in terms of execution here. Great. So what it would look like in terms of direct connections, it would take a second here. Pooled connections would take 20 seconds here, and improvements would be 5x as compared to the baseline, which is no connection pooling at all. And once you have the code for this and you'd like to just deploy it and run it locally, basically what you can do is you can modify these fields and say, what if I have too many queries and a smaller number of threads? Or what if I have, less number of queries and a lot of threads? What would that look like? What would those metrics look like? And basically it would help give you an overview. And this is great for you to visualize for your applications and your needs specifically, just kind of as a guiding light here. Yeah, great. So that was connection pooling. Now let's jump over to caching. Caching is a very great way to kind of help optimize all of your applications very quickly specifically for data that is queried very often. So caching is used on many different sides, but here we're specifically talking about database caching. So, okay, so what would you do without caching? Basically, any data that is, frequently accessed it can cause repeated database queries, and it can create an unnecessary load. And what Redis caching can do here is store those frequently accessed data in memory for really lightning fast retrieval. So what happens is, say, if you have social media and there's a celebrity who's maybe releasing an album or starting in a new movie, maybe folks will want to check out a specific video on their Instagram more so than, say, other folks on Instagram. What that application could do in that case is just cache that video so that every time a request was made for that person's profile and that specific video, it could be retrieved from cache, would be a lot faster than actually going through and hitting the database queries and finding those assets and loading it for the users and for multiple users at the same time. So without caching, as you'd imagine, what would happen in your application is you'd open your connection request, you'd execute the query that the user had specified, just return the results and close the connection request. Again, repeated database queries here, a very high database load and very slow response time. Now, with Redis caching, what you can do is you can check the cache first and then fall back to the database. So what you'll do is, you have the same function, get user's profile. So say, the person is looking for a profile. Let's first check if this is a celebrity and if they're already in our cache. So what we'll do is we'll just first look with our cache key, and that'll be the user ID. Check the cache first. So you, go to your cache data. You have your Redis client. You just retrieve the from your cached key that you had earlier. And if this cache data exists, then you return the entire JSON load, and then you were able to exit this function fully. Otherwise, you were basically going to execute what the prior function was going to execute. So you create that connection request, you execute the query, you have the results, you close the connection, and then you cache the results there. So basically as you cache the results, you can define these parameters per your needs, right? So 300 here basically means a 5-minute delay there. So, and it can return it in the JSON dump that you'll have in the full results. So the benefit here is that it's lightning fast, and cache is basically a lot faster of a retrieval than the database because it is already stored and it's just looking to retrieve rather than figuring out all of the joins and the other logic that it has to do to be able to retrieve data. It also reduces the database load and offers better scalability. So let's just quickly look at cache performance. What we have here is so this is the hour of the day and this is the cache hit rate. So as you're starting up in the morning, the cache may be a lot lighter than it would be at the end of the day, and that's just because the threshold with which folks are searching for a specific user ID here is a lot less. Then what happens is your internal microservices understand, okay, there's a celebrity or there's a few celebrities that people are hitting a lot more on this particular day. So let's start increasing the cache value, the basically the cache capacity here with all of those values. So the hit rate starts increasing as the day goes on, and then you'll kind of come and stabilize. The other important thing to note here is a cache is not a database. So basically what I mean there is it should not end up holding all of the information your database already holds. So what cache should be doing is only holding the most frequently accessed data and not all of the data. So you do need to have some sort of logic in there to help basically start cleaning out a lot of the data that is not as frequently accessed anymore. It could be that, you know, the celebrity people were searching for, their movie has passed, their albums have passed, and now they're not on the top search list. So then the cache needs to be cleared to make room for other new data. And here's a quick demo here. So just basically showing you a quick cache hit rate at 82%, and average response time of 0.003 seconds there. Yeah, so that's another thing I would definitely urge you to look into adding onto your application right in front of your database layer. And the other thing you have to think about doing as you're adding this, and especially as you're looking to scale, is having replications, multiple replications, you know, of your databases along with your cache layer as well, to be able to make sure that, you know, nothing here is going to basically be a single point of failure. So that's for the caching. Now let's talk about the architectural evolution of how SQL applications have gone from the first and early initial phase to how we kind of see them now. Initially, what we see was a single MySQL application, right? So think of a monolithic code base where the database was basically a monolithic database was handling all of the operations. Now, the challenge for this was it's a single point of failure. There's no horizontal scaling, and you have performance bottlenecks here. To phase two, where now you had some replicas. You had some, you know, master-slave replicas here for read scaling. You could see the monthly cost definitely increasing with that, but also the performance increasing with that in terms of QPS. This was still not the most optimized solution. There were still challenges There was replication lag, there was write bottleneck, there was complex failover still happening here. To now adding that caching layer that we just chatted about. So adding the caching layer for frequently accessed data, your monthly cost is kind of a little bit lower than what you see at the phase 2, but your performance has rapidly increased to 20K QPS. There are still challenges. It is not the fit all solution here. You still have to do cache invalidation, like I mentioned, which is basically making sure that your cache stays up to date and it doesn't become a replica of your database. You need to make sure that you're doing memory management, and you need to make sure that you have data consistency. So basically what that means is, say, if in the cache you're storing the user ID for a celebrity as XYZ, but the celebrity actually went and changed their username or handle or something to ABC, you need to make sure you have data consistency also within the caching layer, because otherwise the data will become stale and what it's looking to pull out is no longer relevant or correct. To then moving towards microservices, and basically what microservices are, they take an entire monolithic application and break it into the smallest modular services that communicate with each other. And each of these services is responsible for a very specific business use case. And oftentimes they will have a database attached with them that is very specific to the use case that they're looking to handle. And if you need data from their database, you basically have to interact with that microservice layer to then interact with their database. Now, it is a service decomposition with database per service, like I just mentioned. The cost is quite higher for this, as you're having multiple different services and multiple different databases. But however, it does show up for itself in its performance, where it's the best performance so far from the different architectural phases that we've seen. It does have distributed complexity. It can go through data consistency issues between the different services. There could be network latencies as it's looking to interact with the different services. However, if you're looking at it from a software engineering perspective, having someone ramp onto something like a smaller microservice is a lot easier, because it's so much more granular than having them onboard onto an entire monolithic application. Now, lastly, what we'll talk about is a hybrid architecture. And this is basically the right tool for the right job, whether it's using MySQL, NoSQL databases, a combination of both, along with your microservices. Maybe we extend this out even further and your application is requiring vector databases. Maybe it's looking at RAG applications. So this would be then a more hybrid architecture, and the monthly cost here is an estimation because it really depends on what the different pieces of your architecture are, but generally the performance is a lot higher, and this is because you're looking at, a diversity of technology added here. You're basically taking the best of each use case and applying it so that your end product is the most optimal that it could be. The challenges here definitely include the team training option, like I mentioned before, operational complexity, operating all of these different technologies together, and being able to understand the differences between NoSQL, MySQL, vector database, any other type of database that you're combining with your applications, and how they're to be interacted with the different service layers that you'll have there. All right. So now just let's look at a few graphs here as well. What we have here is the QPS evolution over the architectural phases that we just saw. So with the single MySQL database, we obviously don't have any QPS optimizations, but as we go on to the different phases of the architecture, we're seeing the performance increase in terms of the QPS, like we had seen earlier. And then the cost evolution, on the contrary, is very similar, where as the performance increases, our cost also definitely increases. This one, the hybrid architecture cost, really depends on what different toolings you have. So it could go higher than microservice, could go lower. Very technology dependent, but generally, as you can see, the pattern is the cost is higher. So what you basically want to do for your application is to find that sweet spot where you are able to optimize for cost, along with the architectural updates for your application there, and then sort of implement that instead of trying to implement the most advanced solution where you wouldn't maybe have needed it, to be able to kind of optimize cost there. All right, now let's dig in further into the cost analysis piece here. All right. So investments versus returns here, right? So scaling MySQL basically requires a lot of upfront investments, but the returns are substantial. So we can let's over here, we'll do a few ROI, return on investment comparisons by scenario. So what you'll have is, so let's say you start off with this very small application. The small application will likely have a smaller percentage of return than, say, a medium or a larger or even an enterprise scale application, just because of the size of it. However, let's also look at the cost breakdown of each of these different things. So the smaller application obviously will have a smaller cost at the end, but then this is looking at the optimized cost and the overall saving, the performance gain, and the ROI. So as expected, obviously a larger enterprise scale applications will have a higher return on investment, but they will also have a higher cost upfront to be able to set up the system. I created a quick calculator here for you to be able to see and do just some back of the napkin math to be able to understand what your upfront cost and what your ROI could look like here. What I have it set for default is 10,000 for current monthly cost, 50,000 for implementation cost. And what that looks like for us is, in terms of performance improvement, I set it up to 10x performance improvement, and cost reduction, I'm looking for 40%. So that's looking at our monthly saving at 4K, annual saving at 48K. Our return on investment is low, but our payback period is about a year, which is not too bad, especially for an application that is looking to start off. What you can do is you can sort of play around with performance improvements. You can play around with the cost reduction that you're looking to do. You can even play around with the implementation cost that it took you to set up your application and the current monthly cost, and just see how the different metrics here change and what you'd be most comfortable with for your application. All right. So now let's dive into a few case studies here. And what we're going to basically be looking at are 3 case studies. I think I'll start with Caliber first. Yeah, so, and these are case studies of companies that have implemented some of these solutions here. So what Caliber is it's a leading fitness technology company that's providing comprehensive workout tracking. It's providing nutrition planning, social fitness features as well. And the platform basically serves over 2 million active users worldwide, with real-time workout data streaming from various fitness devices. So the key metrics they're looking at here is scale, which is 2 million plus active users worldwide. Challenge, it needs to be real time, workout tracking, and social features. So the solution they took was a hybrid architecture with MySQL, InfluxDB, and Redis Cache. And their results have basically been performance was 100x faster in terms of QPS, engagement increased 40%, and their overall app rating was, I think, 4.8 out of 5. So those were some great results that they had on their end there, and they basically their issues were query performance. So their queries had slow aggregation over time ranges. They had storage costs. So basically, it was getting expensive to store time series data, since what they're looking for is fitness tracking data, which has to be time series. It has to be tracked on a certain cadence to be able to show improvement for the end user. Data retention was also becoming an issue to manage the data lifecycle for the users. Analytics, which is a key part of their platforms, was an issue because it was poor performance for fitness analytics there. So these were a lot of concerns that they were looking at before they came in to try to find these solutions here. And basically the kind of the integration and the high level architecture they came up with was they had the MySQL database holding the metadata for the users, the workout, the challenges, and the social data. The influx database, which was the time series database here, which was holding the workouts, the metrics, the heart rate, the calories, and then the Redis caching, which is again just storing the leaderboards, which will be accessed frequently, any real-time updates that were going on, any notifications, any updates, any offers going on that they needed to be able to retrieve and notify the user frequently for that. I actually have a nice architecture diagram for this that lives within the case study section of the GitHub repo. I'd say feel free to take a look at that. And I think that can give you a better sense of how they actually designed their application there. So that was for Caliber Fitness. The next one that we'll look at will be for Currency Cloud Financial Services. So what Currency Cloud is it's a leading financial technology company, and it's providing cross-border payment solutions for businesses and individuals. The company processes over 50 billion in transactions annually across 35 plus currencies. So they're working at quite a large scale. So they're looking at 1 million plus transactions daily, real-time currency conversations with, say, sub 50 millisecond latency, solution read replicas, Redis caching, event driven architectures. Performance is 15x improvement, cost is 60% reduction, and latency is 15 milliseconds at average here. So that's what they were basically looking at. And their challenge was that the currency's core business depends on providing real-time accurate exchange rates for international money transfers. So the platform basically needs to be able to handle any high frequency updates, exchange rates for every second that is going on, global scale. They have a very global scale, right? As we're looking at the exchange rate could be with multiple different currencies very globally. So that is definitely something that needs to be real time. And then regulatory compliances, they're looking at money. So basically what that means is they need to be able to follow all of the compliances, all of the regulatory requirements that are needed through all of the different governments there to make sure that they are being able to kind of do the solution in the most optimized way forward. And they also had cost pressure. So database big costs were growing 300% year over year, which was an issue too. So this is why they needed to come in and sort of help change out their architecture. And what they were, so these were the few issues. The solution architecture that they actually did, and again, this architecture is also available in my GitHub, is they had a few phases of architectural changes that they did. And basically, so I can go through and talk about the final optimized change that they did, which looked like a microservice architecture, as you'd imagine. So they had a rate service, which was just a MySQL database. And then they had a transaction service, which was again MySQL, and then a compliance service, which was MySQL for audit logs. So the rate service is to understand the exchange rates, transaction, to be able to do the transaction, and then the audit logs to be able to be compliant. And this was all kind of behind an API gateway to be able to do a lot of the authentication there itself before having the user kind of come on board onto their platform and do the currency exchange there. And the last one that we'll talk about here is telecommunication, PT Finet case study here. And basically what they are is they are Indonesia's leading telecommunication provider, serving over 50 million subscribers across the entire country there. And the company basically offers mobile, fixed lines, and internet services with complex billing systems that processes millions of transactions daily. So here's their key metrics. They have 50 million subscribers. The challenges are that they have complex billing systems with 48 plus hour processing time, microservices, plus event sourcing, CQRS. So those were some of their key metrics here. And basically what they were looking for was they had really high billing complexity. I think they had 200 plus rate plans at 50 plus discount types. And geographic coverage also, actually, they had about 17,000 plus islands across Indonesia that they needed to be able to serve. Daily transactions were very high. I think it said about 10 million plus billing events were happening. So some of their challenges were complex billing logic, multiple rate plans, discounts, multiple promotions that they needed to handle, real-time processing, immediate billing for prepaid services, regulatory compliances again, and they needed to run at a massive scale. And just looking at their architecture also, they also have a microservice architecture, very similar to what we saw earlier, where their architecture looks to have multiple MySQL databases there, one for subscribers, one for billing, and one for payments. And each of these services, each of these databases lives within a service, and the service is responsible for the communication with this database. And this basically lives behind an event bus, like you can think of Apache Kafka, that's ingesting requests and able to redirect them to the correct service there. And what we can see is the performance has improved for all three case studies here. For the fitness app, we see 100x faster queries, 40% increase engagement, a 4.8 rating on the App Store. For the telecommunications, we see 12x faster billing, 99% accuracy, processing time 4 hours. And for the financial services, we see 15x improvement, 60% reduction in cost, and latency is at 15 milliseconds average, which is great, which is a near real-time threshold, which is perfectly great in terms of performance. And just kind of to showcase this in a visual sense. So in terms of performance improvement, Caliber, the fitness app, saw the most improvement here, especially with their hybrid architecture and their time series data here, whereas the others used a microservices and read replicas plus Reddit caching event-driven architecture. And you can see their performance improvements kind of comes at a lower than where the hybrid architecture itself. In terms of cost reduction, we can see all of them basically having great cost reductions overall. So what that says to me is it's very use case dependent which architecture you choose, but whichever you choose, it does seem like you will have a great cost reduction for your application than just using a single MySQL database with none of the optimization strategies that we discussed earlier. And now lastly, I have a quick interactive demo, just kind of showcasing all of the different things we talked about today. And basically what this is it's like a kind of an implementation of what you can do as an hands-on experience. So let's look at the performance simulation first. So the performance simulation for a single MySQL database application, there's the response time, the QPS, the load. Now let's switch it out to say having a hybrid architecture, right? Way better response time, better QPS, better load. You can also change the load and then see how it will work, and that will be your performance simulation. I would urge you to play around with this and figure out what your load looks like and what your best response time could look like based on which architecture type you choose here. And then we have the cost calculator as well. So, you can put in your current users, your annual growth rate, and you can calculate the cost there. So it can recommend that the approach for you is maybe a microservice and your monthly cost is this much and your ROI is that much. So then you can decrease your monthly cost and then figure out, and it's going to recommend the same thing as earlier. I'd urge you to again play around with this. And then I made a kind of build your ideal architecture layer here, where let's start with the default setting, which is read replicas. You'll have table partitioning, a cache layer, obviously load balancer monitoring, and you can set your cache TTL in minutes here as well, and it will generate an architecture for you. Your architecture, it'll say is this, and basically it'll help state what your QPS is going to be here too. So that's basically the overall that I had to share for MySQL. I would again go back and say the best thing to do here is to try within single store's environment itself, make you sign up and make use of the free credits that you get. You can do so much more than just play around with MySQL databases. You can make AI applications, and we've made many before. There's quite a few links to webinars before too where we've done that. So feel free to take a look at that, and happy to take any questions that you may have. Over back to you, Yukti.
All right. So that was an amazing demo. Thanks for putting this together. It's actually very different from what you
Yeah.
have like put together in the past. So it was very interesting to see. I'm actually very curious, like how are you presenting this? Like this
Yeah,
is your Chrome browser or like
yeah,
how
yeah,
is the
yeah. So this is an application. I'm running it locally in my IDE, and I'm just deployed it with Streamlit. We've used Versal in the past as well, and it's just running on my local host.
awesome. Okay. So
Yeah.
yeah, this is something that I've never seen before, like especially on our webinars. So yeah, that was interesting. So folks, we are officially open for the Q&A. If there's any questions, please, this is the time to ask them right now. If there's like if you can't ask them right now, if you join late, we will be sending the recording, and you can always follow up on my email. You can DM me on LinkedIn. You can also talk to Vinija, I guess. So, yeah, if there's no questions, Vinija, I think we can close up early then.
Okay, perfect. Sounds great. And yeah, feel free to connect on LinkedIn if you have any further questions, but thanks everyone.
Yeah, so thanks everyone for joining, and we have amazing webinars that are going to be coming up in the future. So next week we have another webinar, I think on 30th. So I yeah, like I think you can go to our events page and check that out. And like please feel free to sign up, and if there's any feedback, any questions related to today's session, please feel free to email me at team@singlestore.com. You will get a email with the entire session's recording, and if there's any resources, Benija, if you can share the GitHub repo with me, if
Absolutely.
you're okay to make it public,
Yeah,
I'll be sharing
public.
it with everyone, and there will be a link to sign up, and it will entirely guide you to how to get started and everything. So yeah, you'll have like your little toolkit. So yeah, thanks everyone for joining, and have a great rest of the day. Take care, everyone.
Bye-bye.
Bye.